When we calculate fluid pressure against a flat dam wall, the math is straightforward because the pressure vectors all point in one direction. But what happens when that surface curves? On a curve, the push of the water is constantly changing its angle. Solving this directly requires grueling calculus at every point. To save our sanity, we use a beautiful trick from physics: decomposition. We break the complex curved force into a horizontal shove and a vertical weight. First, let's look at the horizontal force. Fh. Imagine you are looking at the curve from the side, through the eyes of a fish. To the water, this curve feels exactly like a flat vertical wall of the same height. So, we use our standard formula, ρ(g)hca. Next is the vertical force, Fv. This is even more intuitive. It is simply the weight of the fluid sitting directly above the curve. For a concave surface, the water rests on top, but for a convex surface, the water is underneath, pushing upward. Once we have these two perpendicular components, we find the total force using the Pythagorean theorem. Let's apply this to a real scenario: a circular quadrant gate in a dam with a radius of 5 meters. Step 1, the horizontal force. If we project this gate, we see a rectangle 5 meters high and 1 meter wide. The center of this rectangle, its centroid, is halfway down at 2.5 meters below the surface. Plugging in our values, density, gravity, depth, and area, we get a horizontal force of 122.63 kilonewtons. But where does this force actually push? We calculate the center of pressure, HP, for our rectangle. It acts at 3.33 meters deep. Now for the vertical force. We need the weight of the water sitting inside this quadrant shape. With a volume of about 19.6 cubic meters, the total weight, the upward force, is 192.62 kilonewtons. Where is the center of gravity for this slice of water? For a circular quadrant, it's located at 4r/3π. Now, let's prove something fascinating. Does the net force pass exactly through the hinge at point O? The horizontal force, Fh, tries to rotate the gate clockwise. Its moment is force times distance from the hinge. The vertical force, Fv, pushes up, trying to rotate the gate counterclockwise. Its moment is its weight times its distance from O. Look at that, the moments are identical, they cancel out perfectly. This means the net force passes directly through the hinge. If we combine Fh and Fv into a single resultant force, we see it pointing right at the center of the circle. Why did this happen? It's not a coincidence. On a circular surface, the pressure at every point is perpendicular to the curve. And by definition, any line perpendicular to a circular arc must pass through the center of that circle. This is why engineers use circular gates in dams. By placing the hinge at the center, the water's pressure creates zero torque. To solve any curved surface, project it horizontally for Fh, calculate the weight above it for Fv, and remember that for circles, all paths lead to the center.